My talk will be devoted to Nobel Prize, which was awarded in 2012, last year. And this prize was awarded for experiments in optics and atoms. And I came from the Lebedev Physical Institute, which is not far from the Institute of Experimental and Theoretical Physics. And in our optical department at Lebedev Physical Institute, we produce some experiments with cold atoms, which is not exactly coincide with Nobel Prize, but very close to such an experiment. And this is a view of some experimental set. You see many optical elements, and in the center there is a glass box about 1.5 centimeters width and about 7 centimeters high. And in some center, shined by several beams of lasers, we can trap atoms, that is rubidium atoms, that is cloud of cold rubidium atoms, and we can make some experiments with these atoms. And another view of experimental set with another trap in Russian, lavushka, trap for atoms, trap for thulium atoms. And again, you see many optical elements, mirrors, lasers. More than 10 lasers are required to perform the experiments. And that is the photograph of a spot which consists of about 1 million cold atoms. The size is less than 1 millimeter. The temperature is about 100 microkelvin without any external helium cooler. However, we are going to Nobel Prize of last year. It was awarded to Serge Haroche and David Wineland with the definition for what it was awarded. You can translate it yourself, but let me do it in Russian. За новаторские или прорывные экспериментальные методы, позволяющие измерять и манипулировать индивидуальные квантовые системы. So the center of this experiment, which we awarded, is individual quantum system. And it happened that Serge Haroche in France with his team made some exciting experiments with photons. Photon serve as an individual quantum system, while Wineland in United States performed experiment with single ions. And ions were the individual quantum system, and they used some possibilities to control and to measure these individual quantum systems. And today I will talk about experiments of David Wineland, and if everything will be okay, tomorrow I will talk about experiments of Serge Haroche. David Wineland and his team for many years works in National Institute of Standards and Technology, well known abbreviatura NIST in Boulder. And again, he performs many experiments with single ions. First of all, how to keep single ion in order to make it possible to address the single ion, to control it, to measure, and so on. It is used, the main device to keep the single ion is so-called Paul trap. Paul, that is the name of a famous German physik who got his Nobel Prize for trap labushka, for charged particles in 1988. It approximately looks like that. There are several schemes of traps, but the most simple one is shown here. That is 4 wires. 2 wires are subjected to radio frequency, the same signal, radio frequency signal is applied to these 2 wires, but another 2 wires are cut, and they consist of 3 sections, and we have different constant voltage on these wires. So in Z direction there is a constant potential with a well where ion can be trapped, but in X and Y directions there is only effective potential, which is dynamic potential, and charged particle can be trapped in the center. The theory of such traps is well developed, and we can change many constructions to make it more convenient for making experiment. This trap is very good for pushing light to trapped particles, because we have some space for laser beams. This is an example of trap, linear trap, which consists of several sections, and so we can trap a chain of ions along the z-axis, and when we shine it with the laser light, we can collect fluorescence from each ion, and we can collect this fluorescence signal for a long time, because the ion can live in this trap hours, not a problem, and repeatedly the ion absorb photons from laser and emit photons as a fluorescence photons, and by ordinary CCD camera we can observe the individual ions as bright spots, and so it's a good tool for further experiment. This is one photograph from experiments of Weiland with a spot that is single ion. In that case, it was a hydrargyrum ion, singly charged. And what is the interest for researchers to look for properties of ion and to make a spectroscopy of ion? It's unique spectroscopic object. First of all, ion in the trap can be cooled. So it has only a small amount of kinetic energy to move inside the potential, and the equivalent temperature is in microkelvin scale. I mean the temperature of kinetic movement. So this ion exhibit its electron structure. I mean set of electronically excited levels of energy with good precision. Even narrow lines can be seen with the help of laser sources, and so it's an ideal spectroscopic object without any disturbances from outer space. You can compensate magnetic field, electric field, and the experiments are performed in deep vacuum, so no other particles collide with your ion, and this is a pure spectroscopic object. Some electron transitions of ions has very narrow spectroscopic line, and this line can be used as a frequency standard for making optical clock. And Weiland, with his team, is a leader of making optical clocks with the help of ions in a trap. And that was the main reason why Nobel Committee awarded the prize to him. About some properties of optical clocks, I will tell a few words during this talk. How does it possible to construct optical clock with the help of single ion? First of all, we need to choose two transitions in the ion. That is electronic transition. That means the electron can be excited into one state or another state. We need to choose two electronic transitions. One should be taken as a dipole forbidden transition. If you have dipole allowed transition, then this transition will give you a good amount of fluorescence photons, and the width of this transition will be rather large and not suitable for precise stabilization of optical frequency. So we need forbidden, in dipole sense, forbidden transition, but let's say it will be electronically quadrupole transition. The lifetime of this transition can be about 1 second, or it depends on your ion. You may find examples with 10 seconds lifetime, and that is very good because the width of this transition will be very narrow. And this transition should be used to make a clock. The photons, when we can have some photons spontaneously emitted from this transition in the ground state conversion. And the amount of photons is very low because it is forbidden transition. So we cannot use spontaneously emitted photons as a test whether ion is excited or not. The number of photons is not enough for our technique, and so we need to use some trick to learn is our laser, future laser, in resonance with this forbidden transition or out of resonance. And this trick consists of using another allowed, well-pronounced transition with very good stream of fluorescence photons. When you excite the ion, and then you observe, you have fluorescent photon, and in cycling this procedure, you can have millions of photons to know whether the ion is in the ground state or it is excited. When the ion is excited into clock level, there is no fluorescence because ion cannot absorb the light of pump laser. But when the electron comes to the ground state, again you can have a fluorescence signal. So fluorescence signal show you whether ion is excited or not. And when clock laser is applied to ion, you can judge whether this clock laser is in resonance or out of resonance with this transition. When the clock laser is in resonance with this very narrow transition, then no fluorescence. When your laser is out of resonance, clock laser out of resonance with forbidden transition, then you have a good fluorescence signal, and you know about the discrepancy between frequency of clock laser and ion. And clock laser, you need to have clock laser because laser beam can be divided into several parts and used for any device to synchronize any processes, to calculate time and so on. So the ion serves as a frequency standard, and this the quality of this standard is transferred into laser frequency of clock laser. That is the idea how to build frequency standard with the help of single ion. This diagram taken from the works of David Wymond and his group, and it shows that when there is no resonance of clock laser with clock transition, then the ion is in its ground state, and you have many fluorescence photons. That is counts of photons during some period of time, fixed period. And when your laser is in resonance, there is practically no photons, and so you see the device is very practical. Also, we need to make some tricks to cool our ion, because it can make some vibrational movements within the well of the trap. And there are some possibilities, very effective possibilities to cool the ion. First of all, let's see for the pump laser. You can have a slight red shift of the frequency of pump laser compared to the transition. Slight frequency shift, I mean that you excite only red wing of the absorbing curve. With this level, you have some absorbing curve of absorption, and you excite only red shift of this transition, but the fluorescence will give you photons in the whole line because the kinetic energy of ion contribute to the energy of fluorescence photon, and thus the kinetic energy goes out of ion with the fluorescence, and that is the first step of cooling. And there is another step of cooling. When the ion is cooled enough, its movement in trap becomes very simple. Only few vibrational modes are excited, and that is the sketch of energy levels of this vibrational movement. Let's say I take the simplest movement like that or like that in the trap, and when this movement is excited, energy is slightly higher with and the energy can be scaled with number of vibrational quanta, and so if we tune our clock laser for a short period, if we tune our clock laser to transition from excited vibrational level to unexcited vibrational level, this is the level where no vibration. Then fluorescence, very slow fluorescence, but it exists, it can be used. Very slow fluorescence will convert some vibrational movement into photons, and this level will be empty in some time, and it is the second step to prepare your ion in lowest vibrational mode when there is no energy in vibrations. So without any external cooling, without helium, without liquid helium, and without any additional measures, only by lasers you can cool your ion up to microkelvins, 10 or 100 microkelvins in a trap. Then at least a few words what are the requirements to clock laser which you use, which you force to interact with your ion? Initially, this clock laser should be stabilized itself by primary stabilization loops, and that is the interferometer Fabry-Perot used by Weiland to in order to make a first stabilization loop for clock laser, and that is very interesting device. It happened that interferometer Fabry-Perot can be very stable if you make if you properly construct it, and you see the one mirror of the interferometer and another mirror on the back side of this sphere. This sphere is made from very delicate material which has no thermal expansion coefficients in room temperature, and the sphere is constructed so that when you suspend it in some positions, the gravity acting to the mirrors does not disturb the distance between mirrors. If you don't care about it and use some ordinary suspension and construction of interferometer, gravity will distort your interferometer, and it will be very hard to work. So primary, the clock laser is stabilized by such interferometers. You see its diameter is about 10 centimeters. And that is example again taken from works of Weiland, where two lasers, identical lasers with identical wavelength, are stabilized by this interferometer. One interferometer stabilized laser 1 and another laser 2. That is two interferometer, two lasers. They are coupled to each other, and then we look for the beating between frequencies of these laser beams. We can see what is the stability of frequency in each laser. And you see the beating frequency. It is about part of hertz. That means the coherence time of these lasers is about 10 seconds, and that is very good result. But this result is used as a primary stabilization of clock laser, and the second step of stabilization should be done with the help of ions. And that is example when two laser clocks were made. This is two laser clocks, and then it was a special procedure to compare the frequencies of these two laser clocks. We have no method to learn about frequency stability, but only one is to compare some frequency standards, some frequency stable devices with each other, because this device and this device is on the best level of stability, and we cannot compare with something much better than they have done. And that is a laser based on hydrargyrum ion. That is again a Fabry-Perot resonator, which used or interferometer, which used to stabilize first the laser. Then it is stabilized by hydrargyrum ion. And Weiland built another scheme based on aluminium ion. That is another frequency, another transition, another frequency. But aluminium is not bad for spectroscopy too. And then radiation locked to ion transition can be compared from one laser clock to another laser clock. They can be compared, and the method to compare two different frequencies is very interesting and unique. It appeared about 10 years ago for this method. In 2005, it was another Nobel Prize awarded to Hensch, German physicist Hensch, who invented the method, who developed the method how to compare two frequency standards which do not coincide in wavelengths. And the name of this method is frequency comb. In Russian, частотная гребенка. Frequency comb is a spectrum of some laser, additional laser. It's a laser which produce femtosecond pulses. Perhaps you know that among lasers there are many samples of different. And for example, titanium sapphire laser can produce femtosecond pulses with duration from few femtosecond to 100 femtosecond, depends on your ability to control this laser. And the spectrum of this laser, due to the short pulse duration, is broad and can be even can be made even broader, and consists of laser modes. That is laser modes, and the distance between frequencies of these modes is constant from red to blue part of this spectrum with very high precision, because this frequency can be extracted from the laser. It can be detected in laser and locked to some radio frequency standard. So this comb offers us a set of well-distant spectral lines, and then we can use this additional radiation to compare two frequencies of lasers. Let's say laser 1 have some frequency blue, laser 2 have some frequency red. When you mix by ordinary mirror this radiation from frequency comb and laser, you can observe with the help of ordinary photodiode, you can observe beating between frequencies, and when you measure the frequency of this beating, you have the idea about the distance between laser and one of the modes. Then you have some possibilities to calculate number of mode distances between these two lasers, and then due to this fact you can calculate the ratio of frequencies of these two lasers. And that is the frequency comb, how it looks like when you put a prism, a dispersive prism to make all the components visible. That here is titanium sapphire laser. You see the spectrum of comb is very broad, from blue to red. You don't see modes because there is a million of these modes, and this photograph does not resolve these modes. And that is the photo from our institute. Experiments are made with in the team of Nikolai Kolachevsky, who was a couple of years elected to Russian Academy of Science, being at the age 39. When you compare two frequencies of two different clocks, what is the information you can give? What is the interesting information you can give from these measurements? Weiland made beautiful experiments to learn whether fine structure constant vary in time or not. I'm sure that most of you know what is the fine structure constant. It is called alpha. It's this ratio. This constant alpha defines the splitting of lines in atomic spectra. I mean fine splitting of lines. And if you have some ion, then the frequency of any transition can be calculated on the basis of quantum mechanics, and you have at least 3 contributions to this frequency. One contribution, simple electron contribution, which is scaled by Rydberg constant, that is energy. For hydrogen it is ionization potential, close to ionization potential, that is fixed constant, energy constant. It can be corrected by some universal function of alpha, universal for definite ion. Then you have contribution, a fine structure, and this contribution is scaled by alpha square. And you have even another contribution, hyperfine structure of this energy and this frequency, and it is scaled in additional ratio, that is magnetic moment of ion and Bohr magneton. And by comparing two ions, two frequency clocks with each other, you can have the ratio of frequency which depend on several parameters, and first of all it depends on alpha constant. Weiland made his very complicated, delicate clocks in laboratory, and during a year and a half, nearly 2 years, during 2 years, he measured the ratio of clock based on aluminium and on clock of frequency of clocks made on hydrargyrum. And during this period, they made, you see, only 5 experiments. I want to stress that the experiments are very hard. You need to use several lasers for one clock, several lasers for another clock. You need to have a comb laser. You need to have massive electronics to make loops to control the laser frequencies and so on. That is a heavy experiment. And they made experiments during at least close to 2 years, and you see that the frequency has some tendency. It is not fixed how however, this tendency is less than the precision of experiment, and this data allow to put an upper limit to variation of alpha in time. And look for the result they obtained. They plot the result on the diagram where you have the temporal drift of alpha and possible temporal drift of magneton, which cannot be excluded from data. And the result now shows only this white area for possible variations in time, and that is the final result, a limit to temporal variation of alpha in time. And I want to show you the accuracy. It is a I can't show you something close to such an accuracy. So this value is now is used for many physicists who is thinking about constant variations in time in our universe and so on.
It's a 15.
Weiland and his group were very active in making some compact construction of ion trap. The ion trap, which was shown before, has the size about few centimeters, and now they have constructed the trap, which is about 10 or 15 millimeters size, and that is the some examples of traps they probed in the experiment. This trap is close to linear trap, which I showed you earlier. 4 wires, and the ion should be placed here. Then you can squeeze this distance, and again 4 wires, and the ion can be trapped here. And final construction is very attractive because it is nearly flat. Ions can be placed in some places here. It could be one ion or several ions in sequence. It depends on your desire. That is a photograph of such flat trap. This is 15 millimeters. The trap is here, the space where ion is placed. This device allows to connect it to some with these wires to some radio frequency sources, to constant voltage sources, and so on. And this device should be closed into some vacuum box with very good vacuum, limited vacuum allowed with your technique. This part is shown here enlarged, and that is the place for ion. Again, this device as it was presented by Violent Group. Again, that is the main place of this trap. It have several electrodes, and you need to use some procedures to catch one ion and move it into center where you have where you can apply your laser beams. Laser beams are applied from above. With these traps, Violent and his group, they are planning to make an optical clock with the, which allows you to measure time with accuracy I will accuracy write in frequency scale. The stability of frequency scaled by the frequency is about 10 minus 17. If you have the clock with this accuracy, this clock will lose only 1 second during the period of time 1 billion of years. 1 миллиард лет, 1 секунда. 1 second, 1 billion years. It's a very challenging task to make this device which can be handled by a person, not in a lab on a table, but this device, they are planning to build it. Can be taken into hands and you can perform positioning with the precision of few centimeters if you use this accuracy. Now I want to show how Violent and his colleagues make manipulation of ion as a quantum object. The most interesting example is made when you put 2 different ions in one trap, in one potential. Inside one potential, you trap 2 different ions. In an example, I will show the aluminium ion and beryllium ion. It happens that Violent used aluminium ion. It is very good for optical clock, but this ion is difficult because good fluorescent transition in this ion to check whether the ion is excited or not. This good fluorescent transition does not exist in aluminium. We hardly can have good laser to pump fluorescence and to control the state of aluminium ion. And this forced Violent to find another way how to control the state of aluminium ion, and they put the second ion in a trap. In this case, this is beryllium ion. And look what happens when 2 ions are inside the trap. First of all, they have a fundamental vibrational mode. They are repelling due to Coulomb force, but they are confined by external potential. So they have, that is two mass vibrating varying distance between them, and this is a mutual movement. So vibrational sublevels of energy, which is superimposed on electronic transitions, is this vibrational energy are mutual for both for aluminium and for beryllium ions. And let's say you have the aluminium ion that is a vibrational sublevel, first excited vibration. You can apply to aluminium ion laser pulse, resonant laser pulse. We call it pi pulse because by changing the amplitude of this pulse, we can control what will be the result of this excitation by taking exactly pi pulse. We convert the state of ion from ground state to excited state. If we have 2 pi pulse, by this pulse we convert it from excited from ground to excited and back to ground. And so by choosing intermediate values of amplitude of this pulse, we can excite even superposition, quantum superposition state of ion when both states come into superposition with some definite coefficients which define the weight of ground and excited state. So let's say we have pi pulse, we excite the aluminium ion. Let it be, it is not exactly pi, but the weight coefficient in that is wave function of ion. Alpha and beta are defined by properties of this pulse, and you have a superposition of lower and upper level. Then you can apply exactly the pi pulse which transfer the ion, the rest of contribution into state to upper level. So you can produce a quantum superposition in vibrating levels of iron aluminium, but this is the same for beryllium because that is a mutual movement. So the vibration of beryllium is the same wave function, and then by applying some pi pulse to beryllium ion, you have the superpositional state in beryllium ion, and it is converted superpositional state as for aluminium. At first, in aluminium you had one quantum superposition, alpha, beta. In final beryllium state, you have beta, alpha. That is element of quantum logic, which is necessary for constructing a quantum computer. And by looking for results of these experiments made in violent group, we can see what is the door from our classical world, where we have some classical devices which can be tuned by hands, and we need to use our classical devices to prepare some quantum state of ion. Where is the door when we use classical devices to affect the quantum system? The door is the light pulses of well-fixed amplitudes, and by varying this amplitude, we can affect the state of atom, ion, it doesn't matter, and produce a superpositional state that is genuine quantum state of a particle. So the door from classical world to quantum one is made with the help of this optical spectroscopy. I would say that we have also the door out from the quantum particle to our classical devices, the output door, and this possibility given us by nature allows us to only to learn whether the particle is upper state or in ground state. We cannot have something else, so we can do it with the help of additional fluorescence, additional laser, and I was showing you an example with atomic clock, how to use fluorescence to know whether a particle is excited or not. So it's a door from quantum world to our classical devices, measuring devices, and experiments of Weiland showed us that all the manipulations can be done on an experimental tape, on an optical table with single ions. Thank you for attention.
Thank you. Time for questions. Guys, well, Misha. The most curious guy, yeah.
You mentioned the bound on alpha variation, relative variation of alpha is less than 10 to the minus 17. But it was claims in the literature. There were some claims that from the spectrum of distant quasars, there are some traces of the real variation of alpha. But do you remember to what number it corresponds?
You mean, pardon.
It's my fault.
You mean the spectroscopic experiments?
Yes, it was not experiment, but observation of the spectrum from distant quasars.
Ah, yes.
There were
From
this observation, focus that alpha really varies.
Yeah.
But to what speed of it,
To what accuracy? Yeah. It was two methods to estimate temporal variation of alpha. One method, the light from quasars. This light was emitted billions of years ago, and so it bring us the light with fine structure of the old, of the early time of universe, and the limitation on possible alpha variation was several times larger. Limitation put by quasar observations was larger.
Does it not exclude variation?
Yeah. Another method is very interesting to estimate temporal variation of alpha is to look for result of natural reactor in Okla, that is Gabon, Central Africa. People found their natural reactor, and there is uranium atoms which produce during fission produce some chain of elements, and by controlling the concentration of these elements you can find some reactions which are connected with alpha value, and again the limit put by this observation were not so precise than was shown.
From this Okla reactor, just you had variations, no variations during last 2 billion years. Just from these observations of objects, from very early objects, it's 10 billion years. And what I remember when this guy performed his experiment in Germany during 1 year, it gave exactly the same accuracy as you need just to accuracy was compared with the accuracy of astronomical observation. But if just they promise us to produce watches with the accuracy a few oscillations in 10 billion years, then you can check for sure. Other questions?
On the previous slide, there was a parameterization angle for alpha and beta, and on the previous, and there are some variables which describe theta. Could you please tell what are those variables?
Yes.
Which of them were right in the experiment?
This is a well-known optical phenomena. When you put laser pulse to atom, resonant laser frequency should be resonant to atomic transition, then the result of excitation depend on square of pulse. Square in Russian площадь импульса. Square of pulse is calculated as a product of pulse amplitude of electric field in laser radiation, multiplied by duration of pulse, and this is a product of electric field to pulse duration. That is a dipole moment of atom, H constant, and this is a final square of pulse, площадь импульса, square of pulse, and it comes into coefficients of wave function. If you want to learn about this little bit more, you need to find Rabi oscillations in test books, and Rabi oscillation phenomena is very close to this relation, and all the notion are well written there.
You have mentioned that we are using lasers to determine whether the ion is in excited state, but after we determined whether it is excited or not, do we destroy that state?
No.
It is still present.
It is, I have to answer in two parts. If you look for the precise wave function, you destroy wave function. You are right, it's not a way to keep the wave function untouchable. But if you want to know only are you in resonance with transition or not, the fluorescence is very good. So your question is the question about how can we learn about atomic state by measuring procedure. We measure is it excited or not, and we destroy the wave function.
Okay, I think it's enough. So, other questions?
So as key announcement, everyone who wants to ski today, we should